Alright, silly people, here's the situation. Uh, we're, we've got this initial wave function, psi of x and 0 is a e to the minus ax squared e to the ilx. Um, and we're basically just going to do all of the problem 221 again, except using this as our initial wave function, so we have to find all this junk that was in problem 221. Um, and so I'm not even going to hold you, this problem is awful. Uh, I'm gonna be surprised if I take less than an hour recording this, because it is just such a long problem. And if you haven't watched video 221 yet, I really recommend going and watching that because I'm gonna make a lot of uh, simplifications and variable changes that are you will become like more familiar with the things that I'm doing if you go watch that. So really, like it's going to get heavy in the calculations, but let's just get into it. So we need to find the normalization constant a. So we need to normalize it. So we're doing a squared integral minus infinity to infinity of the square modulus. So it's that, and you cut it off there. The complex thing, they cancel out when you do the square modulus, so you just end up with this little Gaussian here. Set that equal to 1, and then the result of that integral is just root pi over 2a. And so you find that a is 2a over pi to the 1/4, right? Um, so to get the time-dependent version of the wave function, you first have to do the Fourier transform of the initial state. So it's going to be 1 over root 2 pi times the integral from minus infinity to infinity of the initial wave function times e to the minus I kx dx, right? So we have 1 over square root 2 pi, and then there's going to be a 2a over pi to the 1/4 here. Integral minus infinity to infinity. This is going to be e to the minus ax squared, and then there's going to be two factors of x. So let's do minus x times k minus l. Cool. And integrating that. Griffiths suggests that we do the substitution of k minus l equals u for this part, so let's just go ahead and do that, and also start simplifying the prefactor because we're going to move the radical into the 1/4, so we're going to have 2 squared pi squared on top of our pi that's already in there to the 1/4, and so now I have the integral e to the minus ax squared minus ux, and I think even both of these have I on it, so we need an I here and an I here. Awesome. And then this is something that we did in 221. We did a variable change where we defined a variable y, where we had just this root a here. So you take the square root of whatever is attached to the x squared bit. Then you have x plus whatever is attached to the minus x bit, so we have iu up there, and then over 2 times whatever is attached to the x squared thing, 2a. This will be very important later. And so with this variable transformation, we can do the differential of it. So dy will be just square root a times dx. And we can use that to simplify our integral. And so continuing to simplify the stuff out front, we now have a over pi to the thirds 2 pi to the thirds out here. But then also when we make the variable transformation, we end up with a factor of 1 over root a. Yeah, 1 over root a. And then this is now the integral from minus infinity to infinity. You're going to have the e to the minus y squared dy. And then you're going to be left over with this e to the minus u squared over 4a. Right. All this is just like problem 221. So we can continue to simplify. We've got a up here, but we've also got an a squared down here, moving the radical into the 1/4. And then the result of that integral is just root pi. It's an easy little Gaussian integral. And then we are left with this thing over 4a there. So continuing to simplify, we've got 1 over, actually pi squared, moving the root pi in there, over 2 pi cubed a to the 1/4, then e to the minus u squared over 4a, and then we'll finally write it as 1 over 2 pi a to the 1/4, and this is e to the minus, and I'll expand the definition of u for the last step. It's k minus l squared over 4a. That's not too terrible. So now that we have that, we can move on to getting the time-dependent wave function, which will be 1 over root 2 pi, and it is pretty much the inverse Fourier transform of the Fourier transform. So we have 5k here, and then this is going to be multiplied by exp ikx minus I h bar k squared t over 2m dk, right? So now we're looking at 1 over square root 2 pi, as well as a 1 over 2 pi a all to the 1/4. And then in the integral, we'll have a bunch of exponents. We're going to have an ikx, we're going to have a minus k minus l squared over 4a, minus I h bar k squared t over 2m. Now, whether or not Griffiths wants us to use the u substitution at this part, to me, is unclear. But I ended up not using it because I think it is a silly thing to do at this point. So I'm going to simplify the stuff out front and expand the square that's in there. Just working on the integral. So inside the 1/4 now, we'll have a 1 over 2 squared pi squared 2 pi a all to the 1/4, and then this integral is now looking like exp ikx minus 1 over 4a k squared minus 2kl plus l squared minus I h bar k squared t over 2m. Right. So now here we have 2 to the third, pi to the third a, all to the 1/4. We can actually move the e to the minus l squared over 4a out of the integral because k isn't attached to it, so it's not going to contribute. But then now we have to group it together by factors of k, so we'll have all the stuff which is attached to minus k, and that is going to include minus ix as well as minus l over 2a, right, because 2 over 4a is 2a. Awesome. And then also group together the stuff which is attached to minus k squared, which is going to be IH bar t over 2m plus 1 over 4a. Right. And then that's the sort of integral we're doing. So this is another complete the square type of integral. So again, we're going to define a variable y that's going to look insane. So we want the square root of whatever is attached to k squared. So it's square root of IH bar t over 2m plus 1 over 4a, right? Pretty crazy stuff. And then in here we'll have k plus whatever is attached to the k bit. So we have minus ix minus l over 2a. And that is over, oh, my tablet works now. No, it's over 2 times this junk. So it's IH bar t over m plus 1 over 2a. Right. Awesome. Let's simplify this a lot, shall we? So let's factor out 1 over 4a, 1 over root 4a from the radical. So in here we'll have 2a IH bar t over m plus 1. That's a pretty cool thing to have. And then this is k minus, let's just multiply everything by 2a up here. So we have ix times 2a minus l over 2 IH bar a t over m plus 1. Yeah, that'll do it. And this quantity is interesting because in 221, Griffiths defined this as gamma, so it's 2 IH bar a t over m plus 1. So what we actually have is looking like 1 over root 4a, and then this is gamma, and this is k minus, and there should be a plus here now that I think about it. So it's 2aix plus l all over gamma squared. That's pretty fancy. And so that's why if we do the differential, we just get gamma over root 4a dk, and we can plug that into our integral now. So we have 1 over 2 cubed pi cubed a all to the 1/4, and then it's multiplied by 4a over gamma to change the variables over. We still have the e to the minus l squared over 4a. This integral is going to look really fucking weird because it's just going to be e to the minus y squared dy. I guess the integral isn't that weird, but what comes after, what's left over, is this ugly looking term, which is minus ix minus l over 2a to the squared, so all that squared, and then over 4 times IH bar t over 2m plus 1 over 4a. That's how you complete the square. So let's keep simplifying. We're going to move the 4a into the 1/4 bit, so we're going to have 2 to the 4th a squared in there over the 2 cubed pi cubed a. We'll leave the gamma outside and we'll have this thing. The result of the integral is just root 4 pi, and then we'll simplify this last exponent term by moving the minus sign out and multiplying everything by a. So we'll have a times ix plus l over 2a squared all over, just going to move that 4 in there. This is now 2I h bar at over m plus 1 again. So that's going to end up being gamma squared. Pretty cool stuff, that. So we can simplify the stuff in the 1/4. We've got 2a over pi cubed now. And we can even move the root pi in there, so there's going to be a pi squared here. 1 over gamma e to the minus l squared over 4a e to the a times ix plus l over 2a squared over gamma squared, right? 2a over pi, the 1/4 over gamma, and then these two crazy exponents. If all you care about is answer to this question, leaving it in this form is actually, I think it's a pretty intuitive form to leave it in, but Griffiths does put it in a form that he finds useful for some reason, and so I'm kind of going to treat this as a proof of his form, and it'll be just a bit of algebra. So I don't have to write the 1/4 thing over and over again. I'm now going to define a variable which I'm going to call chi for no reason, of just the prefactor thing. Chi is a lot simpler to write than all that. So we've got chi, and what we're going to do here is, first of all, we're going to expand the square term. I think that's our best course of action right now. So we'll have e to the, let's just write exponent, 1 over gamma squared a times minus x squared plus l squared over 4a squared plus 2x I L. It's not times 2 anyway, but there is an a on the bottom. So that's interesting. We're going to try to make the two exponents have the same denominator so we can add them up in the end. So we're going to have this a over gamma squared thing that we're going to keep working with in a second. ILX over a is how I'll write it. And then we'll have this minus a over gamma squared, and this is going to be L squared over 4a squared times gamma squared. So I'm actually going to expand the definition of gamma here. Plus 1. Right. And then let's collect all the terms into one square bracket. So we're going to have minus x squared plus l squared over 4a squared plus ilx over a minus l squared over 4a squared minus l squared over 4a squared times 2i bar at over m. Yeah. That should be everything. So this term does cancel out this term, right? Um, and now I actually want to factor some minus signs out. So we'll have a minus a over gamma squared. This is going to be x squared minus ilx over a minus l squared. I'm going to try and actually do this multiplication now, as much as it pains me. It's going to be l squared I. It's going to be a plus sign overall. H bar t over 2a m. Awesome. That's pretty cool. Let's now just keep the x squared outside and then move everything else away. So we have minus, we'll do plus a over gamma squared ilx over a with a minus, no, it's a plus sign, minus l squared I h bar t over 2am. And then we're going to expand the square of x squared. This is going to be pretty funky. So we're going to have minus a over gamma squared. And we want to add a few terms in here and then subtract them elsewhere. And the terms we're going to add are minus 2h bar x lt over m plus h bar squared l squared t squared over m squared. And then we're going to have to add those back in down here. So we're going to have ilx over a minus l squared ih bar t over 2am plus 2h bar x lt over m minus h bar squared l squared t squared over m squared. And now I'm thinking that I actually got those signs wrong. Yeah, this should be plus and this should be minus, but they should be fine now. Okay. This is all in the same exponent, by the way. It's getting hairy. So now we can actually group this together into one squared like polynomial. So it's going to be minus h bar lt over m all squared. That was the point of that. And then we're going to move the a through here. So let's just move the a into the parentheses. It's still going to be 1 over gamma squared, but it's going to be ilx minus 2h bar xlt over m minus l squared ih bar. And this is actually multiplied by a now. This is going to be over 2m. This is going to be h bar squared l squared t squared a over m squared. Okay. Now, to simplify that last exponent, we have to do something that's absolutely insane. We're going to factor out gamma squared because we're going to have terms proportional to ilx times 2 ih bar at over m plus 1. You can kind of see that this is multiplied by 1 and you get this term, and then this is multiplied by this junk and you get this term. So yeah, that checks out. And then we also have all of these minus h bar l over, it's actually I h bar L squared T over 2m that we're factoring that out. And it's the same sort of distribution because we have this thing matching up here to the 1, and then this thing times this thing makes this guy. Yeah, that looks good now. So this is gamma squared, so it's going to cancel out this gamma squared and also that one. So I'll write out what gamma is again, or what chi was. It was 2a over pi to the 1/4 times 1 over gamma. This is e to the minus a x minus h bar L T over m all squared times e to the IL. You factor out an IL, but then you have it's just x here, x minus h bar T L over 2m. Cool. So that's pretty funky. And that's the form that Griffiths got as well, so we're matching up to what he did. So now we have to do the mod squared of this now. We have to be careful here because gamma is a complex quantity. So I have to keep in mind that we're taking the mod squared of gamma when appropriate. The e to the IL stuff is going to cancel out when we do the square modulus, but we still have this junk, this minus a times x minus h bar L T over m all squared, and then it's 1 over gamma star squared plus 1 over gamma squared. Right. And then Griffiths defines another quantity w in problem 221, which it ends up just being the square root of a over the mod squared of gamma. So we can go ahead and on the outside turn this into roots 2 over pi times 1 over, or it's not 1 over anything, it's w. We'll have a minus a over mod gamma to the 4th in there to simplify this stupid looking fraction. So we'll have just gamma squared plus gamma star squared, and we can expand the definitions of gamma and gamma star. But this is now just minus w squared times this thing, and this ends up being 1 plus 2ih bar at over m plus 1 minus 2ih bar at over m. These cancel out, so we just have roots 2 over pi w exp minus w squared, and it's minus 2w squared actually, x minus h bar L T over m squared. So it's a Gaussian, right? But it's displaced by this h bar L over m times t. So this is the part where you can interpret, oh, that just means the center of the Gaussian wave packet is moving along the x-axis with a speed of h bar L over m. So at this point we can say now that the velocity of the wave packet is h bar L over m, and rewrite this now in terms of v, which doesn't save us too much hassle, but it's there. Now we need to get the expectation values. So expectation value of x is going to be the integral of x mod squared psi dx. So it's square root 2 over pi w integral from minus infinity to infinity x e to the minus 2 w squared x minus vt all squared dx. And we want to use a change of variables to deal with this. So I'm going to define a y equals x minus vt, so that dy is equal to dx. And we can rewrite this now as roots 2 over pi w. This is now y plus vt here, and this y squared dy. Right. We're going to expand this into two integrals. So we've got integral y e to the minus 2 w squared y squared dy, which goes to 0, and then plus vt integral e to the minus 2 w squared y squared dy. And that's another Gaussian, which has the solution of root pi over 2 w squared. So the 2's cancel out, the pi's cancel out, even the w's cancel out. There's still a vt here. So it's just vt for the expectation value of x. And that makes sense, right? Because the center of the packet is determined by v times t, the time. So that's a sensible result, and we'll keep going. Expectation value of x squared now is going to be x squared times psi squared in the integral. So we've got root 2 over pi w integral minus infinity to infinity y plus vt squared times the e to the minus 2 w squared y squared dy. We can expand that square a little bit. We'll have multiple integrals again. We'll have the integral of y squared dy plus 2vt integral y e to the minus 2 w squared y squared dy plus v squared t squared integral e to the minus 2 w squared y squared dy from minus infinity to infinity. So I'm kind of bad at the y squared integral, but it is just another Gaussian integral. It has a standard solution of root pi over, it's going to be w to the third, root 2 to the third, and then over 2. Yeah. And then this evaluates to 0 because it's odd again. This is v squared t squared root pi over root 2 w squared. Okay. So again, the pi's cancel out and the root 2's cancel out, so we just have so it's 1 over 4 w squared, right, plus v squared t squared. Fancy stuff that's x squared. The nicest part of this problem is the expectation value of p, because we actually have an expectation value of x that is time dependent, so we can use Iron Fist theorem. So we very simply just get mv. Hey, that's momentum. That's kind of crazy. If you want, you can write it as h bar l. And in fact, that's what I'm going to do. p squared is going to be a bit of a bitch because it's going to be minus h bar squared integral minus infinity to infinity, and then this is going to be psi star second derivative of psi dx. So we have to do a couple of derivatives. So I'll expand psi, not psi star, just psi, because otherwise you're going to have a bad time. And this is now looking like del squared, del x squared. This is going to be a giant exponent, minus a over gamma squared, x minus vt squared, plus il x minus vt over 2 dx. So first derivative is looking like, once I get done writing all this shit, just the derivative of whatever's inside the exponent. So we have minus 2a over gamma squared times x minus vt, just plus il, and that's times the exponent, where I don't even have enough room to write it anymore, all in one line, because this problem was designed by Satan himself. That's a times, not, by the way, not an x. I should just do that instead. And now let's do the second derivative. It's kind of not the worst thing in the world, because we're going to have a term which is just proportional to the derivative of this junk, which is just minus 2a over gamma squared. And then there's going to be a term which is the square of this junk, so plus minus 2a over gamma squared x minus vt plus il, all squared, and that's multiplied by the gross exponent. This is such a waste of time. Now let's combine these back into psi squareds and also expand this square by getting rid of the factor of gamma and the 2a over pi thing from before, because now this is the integral of mod squared of psi, but then we just have the minus 2a over gamma squared plus 4a over gamma fourth, and it's 4a squared over gamma fourth, x minus vt squared minus l squared, and then minus 4ail over gamma squared times x minus vt. Right. And then we can expand the definition of psi squared, and we can split this up into multiple integrals as per the usual. So we're going to have an integral which is just minus 2a over gamma squared minus l squared times the integral of just the mod squared of psi. I probably should have written out some prefactors. Let's do that. So the prefactors were just the square root of 2 pi, or square root of 2 over pi times w, right? And then in here, this is now e to the minus 2w squared y squared dy. We're going to have plus 4a squared over gamma fourth integral minus gamma, or minus infinity to infinity, y squared times e to the minus 2 w squared y squared dy, minus 4a il over gamma squared integral minus infinity to infinity y e to the minus 2 w squared y squared dy. And we already know this goes to 0. Such a good integral. It always just goes to 0. And then the rest of the integrals are just Gaussians again. So we have the minus 2a over gamma squared minus L squared. That ends up just being root pi over 2w squared. We got the 4a squared over gamma fourth. That ends up being the really stupid looking term of root pi over 2 cubed times 1 over 2w cubed. Right, and then we'll move the minus sign and we'll move the root 2 over pi into the brackets. So we'll have 2a over gamma squared plus L squared, and that's it. And there should be a factor of w out here that I dropped. I'll just stick it over there. Plus 4a squared over gamma fourth, and it's a minus sign now because we moved the minus sign in, and it's over 4w squared. So let's group it together like this. L squared plus a 2 over gamma squared minus a over gamma fourth w squared. Right. And we're going to take this term and we're going to prove that it's equal to 1 in a different color. So this is looking like 2 gamma squared w squared minus a all over gamma fourth w squared. We're going to use the definition of w where it was root a over mod gamma squared. So we have that this is 2 gamma squared times a over mod gamma fourth minus a all over gamma fourth a over mod gamma fourth. And then you realize that you can cancel out all the a's, and you can multiply everything by mod gamma fourth, so it's all in one line. So now it's 2 gamma squared minus mod gamma fourth all over gamma to the fourth. And then we expand the definition of gamma, so it's going to be just 2 times 1 plus 2i h bar a t over m here, minus, and here it's 1 plus 2a h bar t over m all squared. And then on the bottom it's 1 plus 2i h bar a t over m squared. We can expand these squares because this is now looking like 2 plus 4i h bar a t over m minus 1 plus 4a squared h bar squared t squared, and it's a minus sign over m squared. And that's all over 1 plus 4i h bar a t over m minus 4a squared h bar squared t squared over m squared. So 2 minus 1 is 1. So the top and the bottom are the same, so they cancel out. Equals 1. Which means that the expectation value of momentum squared just ends up being h bar squared times L squared plus A. Very cool. So now we can finally do the uncertainties. So this is the expectation value of x squared minus the squared expectation value of x. We had values for both of these. This one was just 1 over 4w squared plus v squared t squared. That ends up being v squared t squared. So the v squared t squared stuff cancel out. And we get 1 over 2w. Notice that it's the same uncertainty as we got in 221. It's a common theme. Sigma p, much the same sort of thing. And so this is going to be, we just found it was h bar squared times L squared plus A. This is definitely just minus h bar squared L squared. So we get h bar root A. Again, the same as we got for problem 21. So the uncertainty principle is going to remain the exact same as problem 221. Go back and watch it. We found out that it does satisfy the uncertainty principle. So yeah, that should be everything. All right.